Hello, everyone. My name is Jos Visser. I work for Google. My girlfriend's a banker, so that's why I'm wearing a shirt. Not that you have to be afraid that Google is going corporate or anything. I read the USENIX Code of Conduct, and it instructed the speakers to warn people up front if something offensive was going to happen. So I feel obliged to tell you all that I'm originally from Holland, where we're liable to say sort of anything that comes up into our minds, just so you know. I'm here to talk to you in 20 minutes, which is quite hard for me because I find it hard to be brief, about Doorman. And that is a system that I worked on last year when I was at YouTube, which is part of Google, as you all know, for globally distributed client-side rate limiting. And a couple of months ago, we decided to open source that, so that's now available on GitHub for the entertainment of all. So here's the problem. The problem is we have a bunch of client tasks and they use a shared resource with limited capacity. And there's all sorts of ways to deal with that, server-side throttling, et cetera, et cetera. But in a number of cases, server-side throttling doesn't work very well because the server doesn't have any support for throttling, or you don't want to do it, or in some cases being throttled is a very expensive operation in itself. So what we were looking for in our infrastructure at the time was for a solution that allowed the clients that were talking against that shared resource to throttle themselves. And the specific scenario is that the shared resource was MySQL. And the client tasks were like a variety of our web servers that get data out of that database, and specifically the view count infrastructure that updates the view count. All YouTube users, I hope. So the view count is this number that's at the bottom right. No one exactly knows what that number is, but it's a number and it goes up, generally as people watch more of the video. And we have like a ginormous pipeline that calculates that number, and it de-spams signals and does all sorts of other things. And it writes to the database in bulk. And that would regularly overload the MySQL database. So we were figuring out like how to do that. And the problem is that these clients are blissfully unaware of each other. So they can't throttle themselves very well in isolation of everything else that is happening in the network. Right? So we were looking for a solution for client-side rate limiting to prevent us from getting throttled by the server side. But in our case, MySQL is an example of an infrastructure that doesn't really have good server-side throttling, and we were not willing to build it in. There's other infrastructures that we have that have limited capacity, and in many an occasion, as an SRE, I would have to talk to the software engineers and tell them to slow it down a little bit. The solution we build is cooperative, because it's not the case that our clients are malicious. Like, we have all sorts of infrastructure for dealing with malicious clients that try to overwhelm the infrastructure. This is not for that. This was for clients that wanted to throttle themselves because they were nice, and, you know, and they only had a limited budget for whiskey to buy us off with if they were being not very nice. But they just didn't know the number at which to throttle themselves. Often these clients had throttlers, like rate limiters on the client side built in, but they didn't know what to set the limit to, because like 100 QPS could be great one day, but not so great the other day because there were other people doing stuff. So they would lead to tinkering with the limits, etc. So, you know, there's no problem in computer science that can be solved with some sort of elaborate software. So, and I had some free time, and as I get older, I do get to do less interesting technical work. This was exactly the kind of problem that I was looking for, and I had an intern. So we set to solving this problem. We managed to hire the intern. She's now in Australia, but for the rest of her life, she will be known as $intern. So what do we do with Doorman is we build an infrastructure that apportions available capacity and then leases it out to the clients. So clients need to go to Doorman and go like, hey, I want like 50 QPS. And Doorman goes like, yeah, okay, here's 40. Go for it. And then after a while, the client would come back and go like, oh, now I want 100. And Doorman would say like, well, you know, here is 100. Good for you. Depending on all the clients on the planet and however much capacity they want and however much there is to give out, each client will get their fair share for some pluggable definition of fair, like using the the tricks of modern software engineering. You can plug in different algorithms that have like a different definition of what fair is. We have two algorithms that work fairly well. One of them is like really accurate and O(n) squared in the number of clients. That's maybe not always that awesome. And the other one is O(n) in the number of clients, but isn't always very fair when there's an oversubscription situation. And if you can code Go, you can add your own algorithms to that. It is then up to the clients to uphold these limits. And like I said, it's not enforced on the server side, although we do have some thoughts of adding a server-side library that the server could link in if they wanted to see if clients came with Doorman-approved capacity. And then using some cookies or mints and some encryption that allows the server to figure out that the client actually got its capacity from Doorman. But these are just thoughts, probably waiting for my next intern to arrive. So in the Doorman world, you run stuff like this: client RPCs, client tasks that regularly need to talk to the Dormant Server using gRPC, Google's open source remote procedure call system, to request and release and report upon capacity. And then using that capacity, uphold it themselves and go to the MySQL server or like the whatever sort of infrastructure you have that has the limited capacity. The Dormant Protocol is quite simple. The client first needs to discover the master. I'll talk a little bit about it later, but basically, because we support master election with replicas, et cetera, you need to tell the client what the potential masters are, and then Doorman will figure out what the actual master is by talking to by talking to a random Dormant server a bit. And then there's a stream of requests where the client says like, hey, I am client blah, and my priority is such and such. And for resource foo, I currently have 50 QPS and I would like 100. Thank you very much. And then the server responds like, well, you wanted 100, you get like 75, and this capacity will expire in this amount of time. In the response, actually, we have two different times, a lease time and a refresh interval. So the lease time is the guarantee with respect to how long you can use that capacity without oversubscribing the server. The refresh interval is the time in which we ask you, client, to please come back to us and ask for the capacity again. So the problem with leases is always, like, if they're really short, then the system converges really quickly in terms of adapting itself to new clients that come online or changed capacities across the planet. But if there's a network hiccup, then you lose the capacity quickly. So if there's a network separation or the Dormant server restarts or whatever, then all these clients are out in the woods. So for that reason, you want to make the lease long, but that has the problem that if the client goes away, it will take a really long time before that capacity can be harvested back into the system, and it potentially takes a long time for the capacity to get, the capacity model to converge on the new situation. So we decided to just give them two numbers. It's like, here it is for 5 minutes, please check back every 5 seconds. And with that combination, as long as clients keep doing that, the model converges quite quickly to global changes. But if the Dormant server goes away or there's a network capacity, the clients don't immediately lose their capacity. So they can keep going for a while without the Dormant server having to be around. And again, since this process is all voluntarily, we don't have to be afraid that clients want to screw us, because if they wanted to screw us, they wouldn't call Doorman at all and just sending a whole bunch of requests. Life is much easier if everyone is just fair. That's also my model for global peace, is to genetically engineer kids to be like fair and honest, and then within like a couple of generations, like this is all good to go. We've reached this in Scandinavia already, and we can basically sort of like roll this out to the rest of the planet. So feel the burn. I can't vote here, so it doesn't really matter because I'm Dutch, which is all great because I don't want Americans to vote in Holland either. Anyway, right. So the capacity that we export through Doorman is a number, and the Dormant server is actually agnostic as to what that number means. Like most of the examples we have, the number means a rate, so queries per second or a query cost per second, something like that. But it might as easily mean the max in-flight transactions, a gauge where you could potentially use it to limit the usage of a transaction pool that you have in MySQL or in some other like sort of situation. We do have some quite nice and specific support for rates in the client library, and we don't yet have that for gauges because that problem just basically didn't come up yet. And we'd have to think about it a bit, how to do that in a really in a nice way. Yeah. So the Dormant client library. So every client needs to link in the Dormant client library. And it exposes an interface where you as the client can say like, oh, you know, here's resource foo. I want to use like 50. And whenever I get a new lease, call me at this callback function. And so then the client library goes off and establishes the communication with the Dormant server. And whenever you feel the need to request more or less capacity, you can call the client library to say so. And whenever the Dormant server deemed it, or the client server communication deemed it, that you got a new capacity lease, it calls the callback and you do with it whatever you want. We currently have versions in Go, Python, and C++. The Python and C++ ones didn't make GitHub yet because we're still working on the port from our internal Google source code to the open source world. And we have got some Java and Lisp versions planned. Why Lisp? Because I work on a huge Lisp code base these days. It's like the 1980s all over again. I remember it well. I was there. You should have been there. It was awesome. Music was great. The client library also has like a really nice helper library, because one of the problems that you have with Doorman is to figure out how much you want. Right? So for a gauge style metric, figuring out what your desired capacity is less difficult, right? Because you can, every time you want to open a new transaction or whatever, you can sort of keep track of it yourself. But QPS-wise, that's not always easy to figure out how much QPS you want. So what we have in the client library is a helper library that does rate limiting. I mean, and rate limiting libraries come like 100 to a dozen or so, whatever we say in Dutch. And a bit weight, etc. What we have one that is smurfed a bit, and you can just call it with weight, and then the library figures out how fast you would have wanted to go if it wasn't in the way. So it uses some funky math to sort of observe your pattern of calling the client library, and it was like, well, you know, depending on what you did, we think you wanted to go at this much QPS, and it automatically requests that from the Dormant servers, and that makes the code examples like really awesome. We got some nice, what do you call it again, decorators for Python, where you can decorate a function with like the Doorman resource ID, and then all calls to that function are automatically rate limited by Doorman. So that's quite funky. That's specifically nice in the Python library. The Go and the C++ library aren't as amazing yet, but we're working on that. So Doorman is a global system for rate limiting. So that means that like resource IDs and client IDs are globally unique, and you can request resources and resource capacity, I should say, on a global basis. That doesn't mean you can't use it locally or regionally, because Doorman is agnostic with respect to what the client, so the resource ID means. So if you have resource IDs that contain a locality name or a continent name or whatever, and you only request capacity within that region, that is something that Doorman automatically supports by virtue of the fact that it supports global rate limiting. In order to support global rate limiting, you can build a tree of servers with one at the root, and then one per continent, and then within the continent, one in every cluster. And capacity will automatically sort of like migrate through that tree to where it's needed. I mean, obviously speaking, if the tree gets larger and deeper, it takes a bit longer to converge capacities. And if you spin up like a new client in a particular location, it might take a bit longer for the capacity to move from the other side of the planet to this particular data center. But in a standard tree, we would expect that to take no more than 15 to 30 seconds, depending on the actual situation. And The Doorman open source library contains a very nice simulation in Python where you can easily sort of like build trees of like arbitrary sizes and build clients with arbitrary resource requests and then see how the system converges quickly. We built that simulation before we built the actual software, sort of a proof of concept. And I was on holiday and had nothing better to do. The Dormant server itself, in each node in that server tree, you have like a root node and a continental node and a cluster node, etc. At each node in that tree, you have one or more Dormant servers. We use etc.d master election to appoint the master within the node, and clients need to find the master in their node with a application-specific discovery protocol. The discovery protocol is not dependent on the master election protocol. So if you change the master election protocol in Doorman from like etc.d to zookeeper, the client protocol would not have to be changed because it's independent from that from the actual master election technology. The Dormant server, so you need at least one server obviously, but that's not very reliable, so you kind of like 3 or 5, whatever you want. The Dormant server keeps its entire state in RAM. There is no exchange of information with the replicas in the same node, and there's also no backing store. Like this makes coding the Dormant server like really easy, right? Because you don't have to deal with any replication state or like whatever. However, if the Dormant server crashes and restarts, or for some other reason you appoint like another master in the group, it means it knows nothing about the world. Like it is from Barcelona in that sense. Let's see if we can spot the over 35s in the audience, basically. Gary's laughing. So it knows nothing about the world. However, if you remember the Dormant Protocol, every time a client talks to it, it says, here is who I am, here is what I have, and here is what I want. So that means if you know nothing, you can just wait for an entire lease period, and within that lease period, you can be sure that every client has either talked to you and told you what it has, or it has lost its capacity. So at most, at the lease period, your picture of the world is completely up to date. If you want to live on the edge a bit, you can wait 2 refresh periods, which is like 10 seconds, and then you know again like what every client in your world has. So we call that learning mode. So whenever the master goes away, there's a little hiccup in the flow of capacity in the sense that clients can't converge to a new situation and new clients need to wait because we can't harvest capacity back, right? But then we're good to go again and the whole system continues. Doorman has a central server configuration that is in YAML. Now the way the Dormant system works, it only needs to have that configuration at the root node. But it is instructive if other nodes have it as well. But in the server configuration, you basically specify these are the resources I have, and these are the capacities that I have for that resource, and this is the algorithm that we use to give out capacity for these resources. The resource identifiers are in the configuration, at least, are glob expressions, like with stars and question marks, etc. So that means you can build one resource template for a whole family of resources as long as you have some sort of sane naming configuration. So in YouTube, we have like a bazillion MySQL shards that are all like identical. So you can have a resource definition that is for MySQL shard star, and then the clients, whenever they start asking resources for shard 1 and shard 2 and shard 3, the server instantiates specific implementations of that resource based on the matching configuration template. It also means that if we have a resource entry for an identity for a resource called star, that by extension, from what I just told you, just automatically works for every resource that you don't have a specific or more specific template for. If you change the capacity, so you change the configuration file, the root node will see that because we keep the configuration file in etcd. The root node sees that and automatically starts adjusting outstanding capacities. If you adjust the capacity downwards after like log n server tree times refresh time or something like that, the whole system knows about the lower capacity. And while it will adapt downwards quite fast. The example we have here, a lease length of 15 seconds, is actually quite low. We typically advise something like 5 minutes, but this is the template that comes from the tutorial, which adapts really quickly to a bunch of situations. So that's why it's set to that. But typically, we would say 5 minutes for the lease length. So we ran Doorman a couple of times and exported some specifics. So this graph shows you the behavior of one client, and it has 2 lines, a red line and a blue line. The blue line is the amount of capacity it wanted, and the red line is the amount of capacity it got. So you can see that basically the red line overlaps the blue line, so this means this client always got what it wanted. And that can mean either of 2 things. Either there was no oversubscription, so we could just fulfill every client, or there was oversubscription, but this client requested less than its fair share, so it got what it wanted. And the guys who asked for more than their fair share got throttled on the client side. This graph shows a situation where we have a spiking client. Again, blue line is what the client wanted, and the red line is what it got. And you see that Doorman sort of follows what the client wanted until the client really spiked upwards, and then Doorman couldn't fulfill it. And you see the red line undercutting the blue line. But what you also see, that while this situation lasted, the red line goes up a bit. So Doorman was busy harvesting capacity from other clients in this system and handed it out to this particular client until it dropped down again. And you have a short period of a similar situation further down the line. This is the global situation. Here the red line is the total capacity that Doorman gave out on the planet. The blue line is the total capacity that all the clients wanted on the planet. And the yellow line is the maximum capacity from the configuration. So you see again that like Doorman never gives out more capacity than the maximum. And when the clients asked for more than that, it just keeps the red line at the yellow line. And you see there's a little bit of undercutting there every now and then. And that happens when a client releases capacity. It takes Doorman 1 refresh cycle to redistribute that capacity to other clients. So some measurements indicate that Doorman typically gets to within 0.5% of the maximum in like sort of a random situation. You can toy around with that a bit. So I told you that the Doorman client library has some magic for tracking the wants of a client, like for observing client behavior and figuring out how fast it would want to go. So in this graph, what you see is the blue line is what the client actually wanted to do, and the red line is Doorman's estimate of what that client wanted. So you see there is a bit more variability here, but on the whole, the Doorman's sort of calculation of how fast this client wanted to go tracks the actual client desire quite closely, and I think that it has a 5% deviation at any point in time, because it lags a bit behind all of this. Right, so we released the piece of Doorman that we sort of have de-Googled on GitHub, and there's a tutorial on GitHub, and this is basically what you do, and then you have a Doorman situation going, including etc.d and like the Dormant Server and master election, and this, that, and the other thing. And we have a small thingamajiggy called the Doorman shell, which allows you to sort of manually say like, oh, simulate, I have this client that wants this much, and I have this client that wants this much, and then you can see what the actual capacity allocations are. So this comes straight from the Doorman tutorial, and this set of statements, I just tried it on my system, actually works. Takes about 5 to 10 minutes to get all the software and compile it, and then you're good to go. So on the GitHubs, not on the Google Doorman, but on the YouTube Doorman, and we have all the trappings of a decent open source project, like the mailing lists and the getters and the this and the other thing. Team consists of Raushanya Maksudova, the dollar intern, now at Google in Sydney, Richard Zopa, who is like back in Poland, and myself, currently in Cambridge, Massachusetts. So if you want to try this out, like by all means, we'd love to like hear from you. Download it, try it out, critique our software. I mean, it's in Go, not big Go fan. So if you hate it, I'm right there with you. We can work on the Lisp client together. So if you have any questions, because there's a lot more that I couldn't say because of like, time constraints, and Liz is just like ready to beat me from the podium. Find me today or tomorrow. I'm the guy in the shirt. I have another shirt tomorrow, but it will be a shirt again. So thank you very much for your attention.